Hi everyone. Today we're going to look at graphing functions in part 2 of our function notation lesson. So let's get right into it and consider this function f at x. Remember, this is when you see f sort of bracket x, that's read f at x equals 3x plus 1. The values of x represent the inputs and make up the domain of the function, and the values of f at x represent the outputs and make up the range of the function. So before we used to have y to represent the outputs and the range. All we're doing now is we're changing the notation and using the function notation f at x. Instead of having y equals 3x plus 1, we have f at x equals 3x plus 1. All this is, I know this looks like this seems confusing, but it just specifies that we are working with functions. So let's keep going. Again, here's the function notation, and here is the x sort of y notation with two variables. And again, the values of the independent variable represent the inputs of the function and are shown on the horizontal axis. So that would be our x's, and the values of the dependent variable are the outputs, and those are shown on the vertical axis. Okay, so it's nothing really different than what we've already done in the previous lessons, except the notation is different. Okay, so let's do a few examples here. So use the graphing calculator to sketch the graph of the function f at x equals 3x plus 1. So really, it's going to be the same thing that you've already used to. So get your calculator on, go to y equals, and that's same as before. Punch in 3x plus 1 and hit graph. Hopefully my window is reset, and there we go. I'm just going to sketch this graph here. There we go. Okay. So again, nothing different except the function notation, and your calculator doesn't really care what you're graphing. As a matter of fact, you can only input a function into your calculator. Okay, you would get an error if you didn't, because it is y on the one side. Okay, so in each case, express the relation given in function notation as an equation in two variables. Okay, so we have f at x equals 7x minus 23. So that would have been in the previous notation, y equals 7x minus 23. G at t equals t squared minus 2t plus 35. So we would have had y equals t squared minus 2t plus 35. Okay, keep going. Express the relation y equals 11x minus 15 in function notation. So again, you just substitute the y for f at x. It doesn't have to be f. It can be any letter. Okay, it can be it could have been a p at x. Okay, equals 11x minus 15. Okay. The graph of the function defined by y equals f at x has the equation y equals 4 minus 3x. Express the equation in function notation. Again, the y does equal the f at x, so we can just substitute that y in for f at x. 4 minus 3x. Okay, let's keep rolling here. So now we're going to get into some graphing. So the graph of a function is shown. So we have some funky graph over here. It looks like it passes the vertical line test, so therefore it is a function. And we're gonna see if we can find some answers here, some outputs. We want to know what the function, what's the output when the input is 5. So in other words, when x is 5, remember this is f at x. So when I input x is 5, what do I get on the output? Well, in order to find out, I have to go to the graph and first of all, find the inputs. The inputs are on the x-axis. So that's 0, that's 1, that's 2, that's 3, that's 4, that's 5. Okay, so when x equals 5, what does y equal? Well, I have to go down to the graph right there, and then I have to go across to the y and read what the coordinate is what the y coordinate is, or in function notation what f at x is. So this would, in traditionally it would be y. So that's -2. So that's it. So -2. And if I wanted to write that as a coordinate, I would write 5, comma -2. And so in other words, when the input is 5, the output is -2. Again, nothing new here. It's just a little different notation. Okay, when x is -2, so what is f at -2? Well, f at -2, again, let me find -2 here. There it is. I go up to my graph. I go across, and that would be 3. Okay, so that is -2, comma 3, right there. Okay, keep going here. F at 4, well, let me try find 4. 1, 2, 3, 4. F at 4 is here. I go down to the graph. That's -1, -1. Okay, write the ordered pairs associated with the above. I did that over here, but that's okay. I'm going to write them again. So that's 5, comma -2. This one is -2, comma 3, and 4, comma -1. Okay. Now, state the values of x if f at x equals -1. So this is now asking the opposite thing. So they're not telling us the input. They're giving us the entire output, and we have to go backwards and find the input. They're telling us essentially they're telling us the y. They're telling us the y coordinate, okay, or the output. But we don't say y anymore. We say f at x. Okay, so I'll do that in red. So f at x, if f at x equals -1, well, now I'm going on to the y-axis and looking at the output, and then seeing where where the x coordinate is on the graph. Well, here's the graph, okay, right there. So there's the input. So x equals, and here's how you write this, x equals 4. That's a 4 when x equals when f at x equals -1. So that's basically the same as this up here, except it's asking it the opposite way. So when f at x equals 3, again, that's the y. F at x equals 3, it's -2. So basically we're doing the same thing we did a second. Oops. We did a second ago, except just backwards. Okay, and then when f at x equals 4, 1, 2, 3, 4. When f at x equals 1, 2, 3, 4, x equals -1, -1. Okay. All right. Let's look at this one. Okay, so use notation in A to make a statement about points A and B on the graph. Well, point A on the graph, well, that would be f at -5 equals 1. That's A. And B, f at what is B here? F at 6 equals -3, I believe. 1, 2, 3, -3. Okay. Write the x and y intercepts on the graph using function notation. Okay, the x and y intercepts, we have actually one y-intercept, of course, and two x-intercepts, and they are right here. There's the x, there's the y, and there's the other x. So I'll write them in green here. So let's look at the x-intercepts first. There are two of them. There's negative, so f at -6, well, it's going to equal 0, right? Because the y-coordinate is always going to be 0 at the x-intercept. And the other one is f at 1, 2, 3, f at 3 also equals 0, okay? Okay, those are the x-intercepts. The y-intercepts, or there's only one. There only can be one, otherwise it wouldn't be a function. In other words, if this graph, let me show you that, if this graph came back this way and crossed the line again, it wouldn't be a function, right? It wouldn't pass our vertical line test. So there's only one, there can only be one y-intercept. And f, and of course it has to be f at 0, right? Because the x-coordinate is always 0 at the y-intercept right here, equals 5 up here. Okay, moving on. Complete the following statements. The domain of f is, well, the domain, so x is bigger than, well, let me see the left boundary here. Left boundary is -6 all the way to 7. Okay, and the range goes from -4 all the way to 5. So y -4 and 5, and except instead of writing y, we write f at x. Okay, same as before. All right, that's it. See you in class, and thanks for watching.